Hello everyone, welcome back to this online class. Today we are going to look at how to solve ODEs of the first order and first degree, and in particular we're going to look at homogeneous ODEs. Now we are given three questions, differential questions to solve. In part A we have 2xy plus 3y squared dx minus x squared plus 2xy dy is equals to 0. And the condition is that when x is equals to 0, y is equals to negative 1. That condition will help us find the value of the arbitrary constant, c. Part B, we have x times dy over dx is equals to x times cosine of y over x plus y. And in part C, we have dy over dx is equals to x minus 2y minus 3, everything over 2x plus y plus 4. So all these equations are homogeneous. I'm going to explain what I mean by homogeneous ODE and then how to solve a homogeneous ODE. So in the solution process, let's start with part A. Part A, we are given 2xy plus 3y squared dx minus x squared plus 2xy dy is equals to 0. I want us to take note that when you talk of homogeneous ODE, homogeneous ODE of the first order, it is an equation that can be written as dy dx is equals to a function of y over x. If you can write an equation in this form, then that equation is said to be homogeneous. Another one, how to verify that an equation is homogeneous, is you check the sum of the powers of the variables in each term. If you find that that sum is a constant value, then you say that the equation is homogeneous of the degree that you're getting, degree of the sum. So I'm going to explain using equation A. Look at here, x is raised to 1, y is raised to 1. So 1 plus 1, that will give us 2. Again, here we have 2. Here we have 2. Again, the variable here, x is raised to 1, y is raised to 1. Add them, you get 2. So look at the sum of the powers of the variables in each term of this equation. You realize that we are getting 2 throughout. It's a constant sum, which is 2. So you're saying, we're going to say that this equation is homogeneous of degree 2. We now know that it is homogeneous. Remember, that sum must be a constant value in each and every term. If you find different values, then your equation is not homogeneous. Another way, is it possible to express dy over dx as a function of y over x or as a function of x over y? You will try that. If again that is possible, then you will say that the equation is homogeneous. So this is how to verify a homogeneous ODE. Now, how do we solve the equation? We start by saying, we make a substitution, remember, by saying let y be equal to u times x, where u is a function of x, where u is a function of x. So that means I can find du dy dx. So this means that dy dx Use product rule. You keep u constant, differentiate x. When you differentiate x, you get 1. Plus now x constant, differentiate u with respect to x. This is product rule. Product rule of differentiation. If I multiply both sides by dx, what am I going to get? So you say therefore dy is equals to u dx plus x du. So these are the substitutions. Where we have dy, we are going to put u dx plus x du, and where you have y, we are going to put u times x. So we are replacing the variable y in the ODE, so that upon substitution, our new equation will be, let me write it here. Now it will be 2x times y, remember here, 2xy, and our y is u times x. So 2x times ux, that will give us 2x squared u. Then 3 times y squared, so you square y, that is u squared times x squared. So this is the same as plus 3 u squared x squared, that's 3y squared, dx, minus x squared, this term, then 2x times y, 2x times ux, that is 2x squared u, plus 2x squared u. You also have to replace the dy here by u dx plus x du. On the right hand side, we have 0. So we have replaced y and dy into the given ODE. Look at our equation. X is common, x squared is common, so this can be factored out. So you can write this as x squared outside, 2u plus 3u squared dx, minus x squared outside, 1 plus 2u times u dx plus x du. This is supposed to be equal to 0. So that this x squared will cancel with this other x squared. Of course, if I divide the entire equation through by x squared. So this will now give us 2u plus 3u squared dx minus, we'll have now 1 plus 2u times u dx plus x du. This should give us 0. I can open the bracket in the second term, so we'll have 2u plus 3u squared dx minus, this one is minus 1 plus 2u times u dx minus 1 plus 2u times x du. That's what we have. Now look at the terms in dx. Those are like terms, we can combine them. So you can say this implies that 2u plus 3u squared, then here it will be minus minus u, then minus 2u squared dx. I've combined those two terms. Then I can see minus x into 1 plus 2u du. This other term. Remember, this was equals to 0. Even here it is equals to 0. So I can now simplify. This means that 2u minus u, that is u. 3u squared minus 2u squared, that is positive u squared dx minus x into 1 plus 2u du, that should give us 0. So this one is now a separable ODE. Separable ODE. So I can bracket this, bracket it, and write separable ODE. So let's separate the variables. I am going to collect the x's and the dx to form one term, and then the other term will be u's and the du. So we'll have dx over u, we are separating the variables, minus 1 plus 2u over u plus u squared du. That should give us 0. So now, you see, this was dx over x, so let me rub it. This should be dx over x, so correction. Remember, we are separating the variables, so u cannot be there. We are dividing by x and also by u plus u squared. So now let's integrate each term. Now, the question is, what is the integral? Let me write it here. The integral of dx over x is the same as writing the integral of 1 over x dx, and that is the same as natural log of x. So that's the first term on the left-hand side. The other term on the left-hand side is the integral of 1 plus 2u over u plus u squared du. Denominator can be factorized so that we have 1 plus 2u over u into 1 plus u du. And so you realize that in the denominator, we have a product of two linear factors. Upon, if you integrate, of course, not easy to integrate the way it is. What you need to do is to use partial fraction decomposition. So we are going to say, we take this here, let 1 plus 2u over u into 1 plus u be equal to a over u plus b over 1 plus u. Remember, in ODE, you must be able to understand all those techniques of integration in calculus 2, because it's an application of what we did in calculus 2. So now when I multiply this equation by the LCM on both sides, we are going to get a times 1 plus u plus b times u is equals to 1 plus 2u. You can just say or. Now this equation is true for whichever value of u that you choose. It is advisable that you choose values of u which are very close to 0, and such that that value will help you eliminate some terms on the left-hand side. So you realize that in this equation, if I put u is equals to 0, the second term on the left-hand side will vanish because b times 0 is 0. We will simply get a into 1 plus 0 plus b times 0 is equals to 1 plus 2 times 0, which is just 0. So this means that a is equals to 1. So we have found a. What about b? I can also say put u is equals to -1. The first term will disappear, so that means we have a into 1 minus 1 plus b times -1 is equals to 1 minus 2, that is -1. Let me write 1 minus 2. So I'll delete that. Should be 1 minus 2. Or simply 1 plus 2 times -1. Our u is -1. So from here, we'll only remain with the negative b is equals to -1. And so you're going to get b is equals to 1. So we have found a, we have found b. So you replace them here. Where there is a, I'm going to put 1. Where there is b, I'm going to put 1. So that our integral can now be written as the integral of 1 over u plus 1 over 1 plus u du. When you integrate this, the first term will give us ln u. Second term will give us ln of 1 plus u. And if you combine these two logs, you get ln u times 1 plus u. That's what you get. Now, what about the right-hand side? The integral of 0 is a constant c. But look at our answers on the left-hand side. This is natural log, natural log. So even the right-hand side, is advisable that you also write natural log of c to make our work easier, because I'm going to get rid of all those natural logs. So let's go back to the integral. Now that we know the answers of each and every term. So here we got ln x minus, here we have found ln of u, then times 1 plus u. The other side we have found ln of 0. Not 0, that's ln of a constant c. We have found ln c. Or let's combine these two logs on the left hand side. We'll have ln of x over u into 1 plus u is equals to ln of a constant c. So when you check exponential on both sides, we'll have x over u 1 plus u is equals to a constant c. Remember, I want us to take note that exponential ln of a, or simply exponential ln of any given number, ln of f of x, is equals to f of x. That's the idea we are using. Because ln and exponential functions are inverse functions of each other. So when you get exponential of the natural log, you get the same function. Also, exponential ln 2 is the same as 2. So that's the idea we are using to get to this solution. Now, our initial, or simply the problem that you are given, was in terms of x and y. So I have to replace u. Remember, this solution can as well be written as x is equals to cu into c times u into 1 plus u. So what is our u? Let's see where we defined our u so that we can replace it. We started by saying let y be equal to u times x. So that means u is equals to y over x. So that's the substitution we are going to make in order to replace u. So we are going to say that put u is equals to y over x. So what are we going to get? X is equals to c times y over x times 1 plus y over x. That's what we have. And this you can as well write as c times y. Simply let me multiply both sides by x squared. Even if I don't multiply the common LCM, I can see this c into y over x plus y squared over x squared. So you can multiply both sides by x squared to get So you can say, or x cubed is equals to c into xy plus y squared. So that is our general solution. Now we need to find the particular solution. Remember, we are given the initial condition. So let me bracket this and call it the general solution. General solution. Now, from that question, we know the initial condition. What are we given? Let's go back. We are told that when x is 2, y is supposed to be equal to -1. So y at 2 is equals to -1. That means when x is 2, y is equals to -1. So let's apply that and see what you're going to get finally. So you can write apply this condition. Apply the condition that y at 2 is equals to -1. So what does it mean? This means that when x is equals to 2, y will be equal to -1. That's what it means. So let's substitute x is equals to 2, y is equals to -1 into this solution. So we are going to have 2 cubed is equals to c, which I don't know, then 2 times -1 plus -1 squared. What will it give us? Or 8 is equals to c into -2 plus 1. Or 8 is equals to negative c. So therefore, c will be equal to -8. Now we know the constant c, and so you can say hence, when you replace that into the general solution, you are going to get x cubed is equals to -8 into xy plus y squared. So what we have found here is called the particular solution. Particular solution. You must know the difference between those two solutions. You realize that in the general solution, you see we have an arbitrary constant, but now in the particular solution, you know the value of the arbitrary constant. So usually particular solution is obtained from the general solution. So that is part A. Part B. Part B. What are we solving in part B? We can go and check. It was x times dy dx is equals to x times cosine of y over x plus y. Now look at this equation. If I divide by x on both sides, I want to write in the form, rewrite in the form, of dy over dx is equals to a function of y over x. If you can get that form, then it means the equation is homogeneous. Of course, here you cannot know the degree, but it just tells you that the equation is homogeneous. All you need to know is it homogeneous or not, so that you proceed and find the general solution. So when I divide this equation by x, I'm going to get dy over dx is equals to cosine of y over x, then plus y over x. I've divided through by x. So this one here is what I'm calling a function g of this one is a function g of y over x. So this tells us that this equation is homogeneous. And so let's proceed and find the general solution. So if I cross multiply, you can say, or we can say cosine of y over x plus y over x, they shall multiply dx, is equals to dy. That's what we have. So now to solve it, we are going to say let y be equal to ux, where u is a function of x. So when you differentiate both sides with respect to x and you cross multiply by dx, you're going to get dy is equals to, of course, let me not jump that step, dy dx is equals to u constant differentiate x, that is 1, plus x constant differentiate u with respect to x. Or when I multiply by dx, we are going to get dy is equals to u dx plus x du. So this is the substitution for the dy, and this is the substitution for y. Those are the two substitutions that we need to make. So let's substitute them here, that equation that I've ticked, so that our ODE can now be written as cosine of u. Remember, u is from here, you get u is y over x. So where you have y over x, that will be u. So cos u plus u dx is equals to dy, which is u dx plus x du. So let me collect the like terms. I will combine this dx and this other one. So you can say, or cosine of u plus u minus u dx. Somebody might ask, why do we have a minus? I've taken this to the left-hand side. So it becomes minus u, and the dx is common. So on the right, we remain with x du. When you simplify, you see this and this will cancel. So we have cos u times dx is equals to x times du. Look at this equation. It is separable for dE. So this is a separable equation. Let's separate the variables. When you separate the variables, we are going to get dx over x is equals to du over cos u, or 1 over x dx is equals to 1 over cos u du, which 1 over cos u is the same as sec u, sec of u, then here we have du. So now we can integrate each term. On the left-hand side, what do you get when you integrate 1 over x? And on the right-hand side, what do you get when you integrate secant of u? So when you integrate 1 over x, you need to get ln x. On the right-hand side, it will be ln of sec u plus tan u. And remember, you must have a constant c of integration. You can either add it on the left-hand side or on the right-hand side, whichever is you're comfortable with. So I could add it plus ln c, so that you can now apply the laws of logarithms to get on the left we have ln x, on the right it will be ln of c times sec u plus tan u. When you take exponential on both sides, we are going to get x is equals to c times sec u plus tan u. Now this is our general solution, but you must replace u so that we go back to x and y. So you can say put u is equals to y over x. That's what you state. When you replace u by y over x, you're going to get x is equals to c times sec y over x plus tan y over x. And so this is our general solution. Remember, the c is an arbitrary constant. You can only know the value of c when you apply some initial conditions. So what you have found here is called the general solution. Finally, part C. Let's solve part C. We have dy over dx is equals to x minus 2y minus 3, x minus 2y minus 3 over 2x plus y plus 4. If you look at this equation, the way it is not homogeneous, but it can be reduced to a homogeneous equation if we make a certain substitution. So, what do? We are going to say that let where we have the small x, let it be equal to the capital X plus h. H is a constant. Where you have the small y, let it be equal to the capital Y plus another constant k, where h and k are constants that we need to determine. So let us substitute, and before we substitute, we need to know the corresponding differentials. So what is dx with respect to the capital X? That will give you 1. Or the small dx, or the dx small is the same as the dx capital. Similarly, dy with respect to the capital Y is equals to 1. Remember, k is a constant. Or dy, the small y, is equals to d of the capital Y. So those are the substitutions. This one, x is equals to x plus h. Another one is here. And even the corresponding differentials, dx is that, and the dy is also this. So that's what we have. Now let's substitute them into our ODE so that our ODE will now be, so the ODE, it will be dy capital over dx capital is equals to x plus h minus 2 y plus k minus 3. This you divide by 2 into x plus h plus y plus k plus 4. And this thing can also be written as x minus 2y plus h minus 2k minus 3. Denominator will be 2x plus y, then plus 2h plus k plus 4. That's what we have. Now, because we said when we make those substitutions, we are going to reduce the ODE to a homogeneous equation. For that to be true, then we expect that where we have the constants, those should be equal to 0. Constant terms should be equal to 0. So that's the condition that we need to impose, that this one should be 0. Similarly, this other term should be equal to 0. So we are going to say let h minus 2k minus 3 is equals to 0. This can be equation 1. Also, 2h plus k plus 4 is equals to 0. So if that is the case, then it means that therefore our ODE is dy over dx is equals to x minus 2y over 2x plus y. This equation is now homogeneous of degree 1 in the new variables x and y. This is homogeneous of degree 1 in x capital and y capital. And now it is easy to solve it because we know how to solve a homogeneous ODE. So look at these two equations. Let's call this equation 1 and this one equation 2. I need to solve these two equations simultaneously to get the values of h and k. So from equation 1, I can use substitution method. Equation 1, we realize that h is equals to 2k plus 3. So now substitute into equation 2. So substitute into 2. Into equation 2. So what are we going to get? We are going to get twice of h, 2 into 2k plus 3. Then I can see there's a plus another k plus 4 is equals to 0, or 4k plus 6 plus k plus 4 is equals to 0, or 5k plus 10 is equals to 0. So from here, If you make k the subject, you get k is equals to -2. So that's the value of k. What about h? H will be equal to 2k, 2 times -2 plus 3. So that's -4 plus 3. That will give you -1. So this implies that h is equals to -1. So we now know the values of h and k. And so those will help us now get our general solutions. So let's go back to the ODE that was homogeneous and see how to solve it. Of course, we are going to make another substitution for us to be able to solve that equation. Now, this equation can be written as, let's start with the dx. So we'll write this as x minus 2y, x minus 2y dx, then minus 2x plus y dy is equals to, I have just rewritten it in another form, rearrange it, cross multiply, and then you rearrange it. X minus 2y dx and minus 2x plus y dy is equals to 0. So we are going to use substitutions. We say let now it will be now u capital, not u, so x capital, y capital be equal to u times x. Everything is now capital, so that from here, remember this is the substitution that you're making. Let me find the derivative with respect to x. So dy capital dx, that is equals to u constant, differentiate x, which is 1, plus x constant, differentiate u with respect to x. This product rule, or make dy the subject. So you can multiply both sides by dx, so that we have dy, let me write that, we'll have dy capital is equals to u times dx capital, then the other one is x times du. So you say plus x capital times du. So this is the corresponding differential. So let's substitute them here into that ODE, so that our ODE can now be written as, we are going to substitute those two into the given ODE. So let's start by replacing the first term. We'll have x minus 2y, where this y we are going to put u times x. So we'll have this x minus 2 times ux dx. Then minus, there's a minus, there's 2x plus y, where we have y, it's u times x. Instead of dy, we'll have u dx plus x du. That should give us 0. Now, if you look at this equation, you realize that x is common, the variable x is common. And so you can factor out the x capital. You can say, or this can be written as x outside. Inside we have 1 minus 2u dx. The other term is minus x outside 2 plus u times u dx plus x du is equals to 0. So the x will cancel. This x will cancel with this one. Or what you do is to divide the entire equation by x. So what do we get? Upon division by x, we want to get 1 minus 2u dx, then minus 2 plus u into u dx plus x du is equals to 0. So look at the dx and another dx here. They are common. So we can be able to combine those like terms. You can say or 1 minus 2u, then minus, of course, I open the bracket here. That will be minus 2u minus u squared. 2u minus u squared dx, then minus x into 2 plus u du. That should give us 0. So, are we able to simplify this one? Yes. This can as well be written as 1 minus 4u minus u squared dx minus x into 2 plus u du. That should give us 0. So what we have there is a separable ODE. So we need to separate the variables. What are we going to get when we separate the variables? So you can write here that this one here is a separable ODE. So when you separate the variables, we are going to get dx over x minus 2 plus u over 1 minus 4u minus u squared du is equals to 0. So once you separate the variables, you go ahead and integrate. So we are going to integrate this term, integrate this one, and also this. Of course, we know how to integrate dx over x. This will give us ln x. I don't need to write so many things like now. Ln x capital minus the other one. The other one, you have to make another substitution. You're going to say let p be equal to 1 minus 4u minus u squared. So we also need to get dp du. dp du, that will give us negative 4 minus 2u, which you can write as negative 2 into 2 plus u. So this means that therefore dp over negative 2 is the same as 2 plus u du. So that integral of this integral now of 2 plus u du over 1 minus 4u minus u squared is the same as now writing the integral of this is dp over 2 over negative 2, I mean, divide by p, which you can write as negative 1 over 2 integral of 1 over p dp. And so when you integrate that, you get you'll get negative 1 over 2 ln p. But what is p? Replace p. So this is negative 1 over 2 ln 1 minus 4u minus u squared. That's what you get. So here is a negative 1 over 2 ln 1 minus 4u minus u squared is equals to, let's say this is 1 over 2 ln c. It's just an arbitrary constant. 1 over 2 ln c. So I can now get rid of 1 over 2. So let's multiply the equation by 2. You can say, or if I multiply through by 2, I'm going to get 2 ln x plus ln of 1 minus 4u minus u squared, 1 minus 4u minus u squared, that's what we have, is equals to the natural log of the constant c, ln c. So you can now get rid of the logarithms. Now you know how to apply the laws of logarithms. To apply them, this will be the power of x, so ln x squared plus the other log. So this can be written as ln of x squared times 1 minus 4u minus u squared. I'm going to write that. Minus u squared. There's a closing bracket which I've not written here. There's a closing bracket is equals to ln c. So now when you take exponential on both sides, we'll have x squared times 1 minus 4u minus u squared is equals to a constant c. So this is our general solution, but we need to go back to the small x and the small y. So we need to perform back substitution. Let's first of all replace the capital U. Let's see where we defined it so that we can replace it. So the capital, where we have capital U, we write U capital is equals to Y capital over X capital. So that's the substitution that we are going to make. So when you replace, what do we get? We are going to get, so you can just write here, put U is equals to Y over X. So we're going to say therefore, or X squared into 1 minus 4 times Y over X. Then you square Y over X, that will give us Y squared over X squared is equals to a constant C. If I open the brackets, we are going to get X squared minus 4xy minus Y squared is equals to C. Again, we need to replace X capital and also Y capital. So check where we defined our capitals. Remember, this is where we started by saying that let the small x be equal to X capital plus H here. and the small y is y capital plus k. So you can make those capitals the subject. So it means that the capital X is equals to x minus h, and the capital Y is equals to the small y plus k. So let's write them here. So here you can just say that put the capital X is equals to the small x minus h. But what is h? H was -1 and k was equals to -2. So this is the same as x minus -1, which is the same as x plus 1. What about the capital Y? Where we have y, it will be equal to the small y minus k. K is -2, we already found that, so it is the small y minus -2. A minus and a minus is the same as a plus. So that would be y plus 2. So finally, when we replace, let me remove that. When we replace this and the other one, we are going to get or x plus 1 squared. Now it is the small x minus 4 times x plus 1 times y plus 2 minus y plus 2 squared is equals to a constant c of integration. So what we have found here is our general solution of that given ODE. General solution. So thank you all for watching this video. Please subscribe to my YouTube channel, that is Professor Francis Okech. If you go to the YouTube search, type Francis Okech or Prof. Francis Okech, and you will find me right there. Also, don't forget to comment, like, and share this video. When we meet next time, we look at more problems in the solving ODEs of the first order. Bye-bye.